Hello there, Charger people. It's Mrs. Boyd again. Today we're going to talk about some new rules for congruence that we haven't talked about before. So previously we've talked about side, 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 and side, angle, side. Well, today we're talking about ASA, or angle, side, angle, and AAS, angle, angle, side, congruence. We're going to start with angle, side, angle. Triangles can be proven congruent when two angles, and the included side are congruent to two angles in the included side of another triangle. So triangles can be proven congruent when two angles and the included side. So that means if it's angle A and angle B, then it's the side between them, side AB. So that means angle A would be congruent to angle E. Angle B is congruent to angle F. And side AB is congruent to side EF. If those three things happen, angle, side in the middle, angle, then we can say that triangle ABC is congruent to triangle EFD. Let's put this to good use with some proofs. Our first statement is that side AD is parallel to side BC. We can see that because of the arrows here. And angle BCD is congruent to angle ABD. So BDC is congruent to ABD. BDC. Ooh, got that wrong. So let's mark that on our figure here. BDC is congruent to ABD. We eventually want to get to triangle BAD is congruent to triangle DCB. So now we know that we have two angles that are congruent. We also know something else. We also know that angle DBC is congruent to angle BDA. So let's mark that. These two guys are congruent. Let's write it down here. Angle DBC is congruent to angle BDA, and that's because of the alternate anterior angle theorem. Okay, opposite, we have two parallel lines and a transversal. If they're alternate anterior lines, they are, or angles, they are congruent. Then we have, we've said this a bunch of times, if we have two triangles, like we do here, and they share the same side, we can say that segment DB is congruent to segment DB because of the reflexive property. And finally, we can say that triangle BAD is congruent to triangle DCB. Let's see how we know. We have an angle here at the top. That's an angle. We have an angle here, and the side in between them, DB, is a side. So we can say this is because of angle, side, angle congruence. Let's try another one. We have angle E is congruent to angle H. J is the midpoint of EH, and those are all given. Well, let's do the obvious first. If J is the midpoint, that means EJ is congruent to HJ. So segment EJ is congruent to segment HJ, and that's the definition of midpoint. Then we have number 3, we can say that EJG is congruent to HJF, Let's put that on our list here. Angle EJG is congruent to angle HJF because of the vertical angles theorem. And finally, we can say that triangle EJG is congruent to triangle HJF. Let's see how. We've got an angle here, sides congruent here, and angles there, and it's because of angle, side, angle congruence. Let's do a few more. I'm hopeful these are starting to make some sense in your brain as to what we need to prove. We have angle K is congruent to angle PQN. So angle K is congruent to PQN. LQ bisects KP, and LQ is parallel to NP, which we can see by our arrows. So let's first say that, let's see, we have the bisector here. So let's do that one. LQ bisects and KP. All right, so we'll know that KQ, segment KQ, is congruent to segment PQ because that's the definition of a segment bisector. Then we can know, let's see, we can also know, we can know that angle KQL, which is this guy right there, is congruent to angle QPN, which is that guy there, because that's the they're corresponding angles. It's the corresponding angle theorem. So finally, we have triangle KQL is congruent to triangle QPN. We've got an angle here, a side, and an angle. So that's angle, side, angle congruence. One more example, and then we will move it on to bigger and better things. Segment RS is perpendicular to segment SU. We've got right angles here. Segment UV is perpendicular to segment SU. And T is the midpoint of SU. Those are all given things. Well, we already know that angle RST is going to be congruent to angle VUT. Oh, no, I'm sorry. We don't know that yet. We have to know one other thing first. We have to know that angle RST and angle VUT are right angles because perpendicular lines create right angles. Now we can know angle RST is congruent to angle VTU because all right angles are congruent. What else can we know? Ooh, now we can know that RTS, gotta find a vertical angle, and that's VTU is congruent to angle VTU because it's the vertical angles theorem. Last but not least, we can know that segment ST is congruent to segment UT because that's the definition of a midpoint. We haven't done anything with that quite yet. So we know that ST and UT are congruent. So now we have an angle that's congruent, an angle again, and the side in the middle. So we can say that triangle RTS is congruent to triangle VTU because of angle, side, angle congruence. But that's not all we want on this particular proof. We want to prove that segment RS is congruent to segment VU. Well, we can say that's true because congruent parts of congruent triangles are congruent. So SR and UV are congruent parts of the same two triangles, so they have to be congruent. That one's a little involved, but I think you can do it, especially if we were to see this on a homework or on a test, and now we've worked this together. I think you can do it. Let's look now at angle-side congruence. Whoa. This tells us that triangles can be proven congruent when two angles and a non-included side are congruent to two angles and a non-included side of another triangle. So what that means, if we've got angle A that's congruent to angle E, and angle B is congruent to angle F, then we keep moving around the triangle and we have segment BC and segment FD that are congruent. You see the side that are congruent are not involved in the middle of these angles. It's a separate whole side. So we can say that, let me figure this out here. We can say that triangle ABC is congruent to triangle EFD because of angle-side congruence. Let's do some problems. We're given that LQ is perpendicular to, or parallel to, NP, which we have shown here in the little arrows. Segment KL is congruent to segment QN. So let me mark that. KL is congruent to QN. And LKQ, angle LKQ, is congruent to angle NQP. All right, so we've got a side and an angle. We have to figure out what else we can say. Well, if we know that QL and NP are parallel lines, we can say that KQL, angle KQL, is going to find an angle that lies along that parallel line, is congruent to angle QPN because they're corresponding angles. Corresponding angle theorem. So we've got a side and an angle and an angle. So we can say that triangle KQL and triangle QPN are congruent because of the angle-side congruence. Let's keep going. This may look like a familiar object, like we've had it before. Angle A is congruent to angle C. Segment AD is parallel to BC, and we can see that from these little arrows here. We eventually want to get to AD is congruent to CB, so we're going to have to prove these two triangles are congruent. All right, so we know that AD and BC are parallel, so we can say that angle ADB and angle CBD are congruent because they're alternate anterior angles. And we use the alternate anterior angle theorem. Now, the one we know and love, segment DB is congruent to segment DB because of the reflexive property. So we can say that. So now we have an angle another angle and a side that's not included. So we can say that triangle ABD is congruent to triangle CDB because of angle side congruence. But that's not where we want to stop with this one. We need to prove that AD is congruent to CB. Well, we can do that because congruent parts of congruent triangles are congruent because AD and BC are congruent in the same triangle. If that doesn't make sense to you, you can look here. This is like our key. A goes with C, D goes with B, and those are in the same parts of our triangles. So those have to be congruent. Two more, and then you're off on your own. Angle S is congruent to angle U. And segment TR bisects angle SRU. So that means this angle and this angle are the same. We need to write that explicitly. Angle SRT is congruent to angle URT because they are the definition of an angle bisector. Now we know that our favorite segment RT is congruent to segment RT because of the reflexive property. So we've got an angle, and a side. So we can say triangle SRT is congruent to triangle URT because of angle side congruence. That also tells us that angle RTS is congruent to angle RTU because congruent parts of congruent triangles are congruent. Last but not least, I hope everything's starting to kind of fall into place for you here. We have angle W is congruent to angle Z. Segment WV is perpendicular to segment VY. And segment YZ is perpendicular to segment VY. Well, let's remember that angle W, VY, and angle ZYV are right angles because perpendicular lines create right angles. Now we can say what seems really, really obvious, that if we have angle WVY, it has to be congruent to angle ZYV because all right angles are congruent. That's a duh to me. Here we have an angle and an angle. Now we need sides that are congruent. Well, we've got segment VY is congruent to segment VY because of the reflexive property. And that's a side. So we can say triangle WVY is congruent to triangle ZYV because of the angle side congruence. I hope this makes all sorts of sense to you. I hope you're doing amazing, and I hope to see you soon.